So welcome to the second talk of Foundations of Data Science series. We are very happy to have Sujay Sanghavi with us today. Sujay is an associate professor at UT Austin. He got his PhD from University of Illinois, and before joining UT Austin, he did a postdoc at MIT. So Sujay works on machine learning and optimization. He has done some groundbreaking work in those areas. And Sujay is right now at Amazon. So he is very interested, as he said, that in learning from and applying his ideas in industry. Before Amazon, he spent time in Google research as well. And now he's an Amazon scholar and principal scientist at Amazon. So welcome, Sujay. We are very happy to have you with us.
Okay, thank you so much for the invite. And this is the first time I'm giving a video seminar, and also it's the first time I'm giving it from home with my kids around me. So, we'll see how it goes. So I wanted to talk today about what I've been thinking about for a few years now, which is to think about how to make models more robust. And so I had done some initial work on making things like, PCA and linear classification and kind of simple ML models more robust. But more recently, we were seeing, the techniques that are used there cannot be used in modern large-scale models like neural networks. And so, we need a kind of different approach. So that's what this talk is about. So please feel free to ask me questions as we keep going. I need to see my own screen. Is this possible?
Yes, can you share your screen?
Okay. Let's see. Yeah, okay. Can everybody see my screen?
And for the audience, if you want to ask questions, please just unmute yourself and ask questions. Otherwise, you can also raise your hand in the chat and type your question, and either Klimo or I will read it to Sujay. Okay, Sujay, continue.
Okay, right. Okay, so jumping into it. A trend that I think all of us have observed is the growing kind of the relationship between larger and larger model sizes and higher accuracy of the resulting models, right? So here is a simple plot of the number of parameters in ImageNet, ResNet style models and their accuracy at 1. And kind of the broad trend is that, we have lots of computing and we have lots of training data, and we use that to make larger and larger models, and we get higher and higher accuracy, right? So this is what is different from, let's say, 10 years ago, when this trend was not really observed or possible. Right? So pretty widely used approach now is, I like to think of it in 2 steps. So if I have a custom, let's say, image classification task that I am interested in, what often makes sense is for me to take somebody else's pre-trained model and fine-tune it for my task, right? So I like to think of it as generalize and specialize. So the first step is to take a large model, which is typically difficult to train and is often trained on either unsupervised tasks or some supervised task that has a lot of training data, even though it is not my task, right? And so you train a large model. Nowadays, what many people do is just download a large pre-trained model from one of the online libraries for such models, right? And then the next step is basically what I think of as specialization, which is to use this model as a starting point, and then make relatively small changes, right? So so we can change 1 or 2 layers. We can maybe add an extra softmax. And we can warm start parameters and then take a few training steps, which typically means stochastic gradient descent, right? And its variance. Let's see. Yeah, so as I was saying, the trend is to use larger and larger models, and which are typically trained by stochastic gradient descent. The issue we're interested in is robustness. And unfortunately, what happens is that for all these models, performance drops drastically if the training data is, I just call it bad, which means that it has some errors, right? And the errors could be either adversarial, or it just could be sloppiness in the data set, or it could be that the data set is not exactly what you need for the task at hand. Right? So just to show this via a simple example, what we did is we took a very standard data set, CFAR10. It's kind of a small data set of images with 10 labels. And we took a pretty standard neural net, which is a wide res net. And we trained it with our samples. And in our training, we got 92% accuracy with the standard CFAR10. Right? This model actually has much higher accuracy. We just did a very basic training of this network for 92%. Right? What I want to emphasize is that this is not robust. So what we did is we introduced what I call systematic label noise. So I took CFAR10, and for 25% of every label, I changed that label to a specific different label. I guess what I was saying is that I took a pretty standard setup, which is a small data set, CFAR10, and a moderate size network, which is wide resnet 16, which on a clean data set has pretty good accuracy. And what I did instead is to change the training data, right, and see what happens with a bad training data set. And the way I made the bad training data is I took every label, took 25% of the samples, and made them something completely different, right? I took 25% of images that are actually trucks and gave them a label of bird, and so on. Right? So as one can imagine, with label noise like this, accuracy would go down. And what we can see is that accuracy goes down pretty drastically. So on the right-hand side, I have a little plot which gives the size of the data set, and it gives the accuracy of the resulting trained model. And we see that while accuracy does go up with the size of the data set, it cannot make up for what it would have been if there were no bad labels. Right? So there are two oracles here, which are the two top lines, and they are super accurate. So this is if we knew which images were in error, right? So if we knew which images were in error, we could get very good accuracy again. But if you do not know which images are in error, then accuracy suffers, and the size of the data set cannot help it. Right? Okay, so this is an example from supervised task, which is image classification. We even took an unsupervised task, which is training a GAN to generate MNIST images, right? So everybody knows the MNIST data set, and we took, again, a pretty standard GAN architecture, which is the DC GAN, and also a pretty standard way to train it. And if we had a clean MNIST data set, this has been known to be able to generate completely new handwritten digit sets. So I've shown them at the bottom over there. Right? But now we can ask the same question of what happens if the training data for this unsupervised task is corrupted. Right? So which means that instead of MNIST, I have a corrupted data set from which I have to generate handwritten digits. Right? So the corrupted data set I have in mind is one in which 80% of the samples are still MNIST, but 20% are not handwritten digits, but something completely different. Right? So in this case, we chose fashion MNIST, which also is a reasonably popular data set. And it's convenient because it has exactly the same format in terms of the number of pixels and so on as MNIST, but is little images of clothes and accessories. So if I have a data set which actually contains 80% MNIST samples and 20% fashion MNIST samples, and I am ignorant of this fact, and I use and I train a DC GAN, then I get really bad quality output from the GAN, which is, essentially consists of mixed images, and the digits don't look like digits, and the clothes don't look like clothes. Right? So the question we want to ask, both in the supervised and unsupervised setting, is if we knew that the data set we're going to deal with is not great, okay, that it has errors and it has corruptions, what should we do differently? Right? That's the question that we hope to answer in this talk. Right? Okay. So the principled approach, which is something a lot of people have worked on, is to design a custom robust variant to your machine learning method. Right? So for example, if you have something like PCA or linear regression, you can design a different way to do regression or a different way to do PCA, which is principled and which is made for the kind of errors you expect. Right? Unfortunately, this kind of an approach is not really tenable when we are thinking about neural networks for large scale tasks like image processing or natural language. Right? And kind of the reason is that getting high accuracy models is hard even with good data. And we lack the kind of deep algebraic understanding that we have, for example, for PCA. Right? And also something which at least I learned from industry is that a lot of these models are often part of bigger data pipelines, and it's not very easy to just replace it with a completely different method. And so it would be better if we could make an existing method more robust. So that brings us to our motivation, which is, can we make, in some sense, any machine learning model robust to bad training data, right? By making minimal assumptions on what we can do with respect to changing the model architecture. Okay, so that's what we call model agnostic. And we have an approach, it's kind of a generic approach, and it applies to any machine learning model where we can do two things. We can train a model or train or retrain a model with a fresh set of samples. And for any given model, we can evaluate a per sample loss. Right? So the two things I need from my setting is that I should be able to train it or retrain it, and I should be able to evaluate a per sample loss. Right? So pretty much any modern machine learning setting you can think of satisfies these two criteria. So just to put some math into it, I assume that there is a per sample loss called L theta. And given a set of samples Si, I can find the best theta for them. And conversely, given any model parameter set theta hat, I can find a per sample loss of L theta hat. All right. So here's a method from, or here's an idea or a method from classical statistics. And it says, and this is a quote from Legendre. It says that if among those errors, there are some that appear too large, then the equations that produce those errors should be regarded as faulty and should be removed, right? So that's the basic idea. And as you can see, it's pretty old. Right? So specifically, there is the notion of what is called trim loss. Right? So the standard approach is to learning a model is to minimize the sum of losses over the samples. And what trim loss does is it tries to fit a model only to a fraction of the samples. So instead of trying to fit a model to 100%, it will try to fit a model to only tau n of the samples. Right? So tau is the fraction that I think of as good or clean samples, and everything else is dirty. Right? So this is a classic idea. It's called trim loss, and it's NP hard even for linear regression. Right? So you can write it as a double minimization, as I have done here, where you want to minimize the sum of losses, but over a set S of size tau n. And so it's a joint minimization over theta and S. Right? And you really can't do much better than exhaustive search over all tau n subsets. Right? So this is trim loss. It has, I mean, even though it's NP hard to achieve, it has been analyzed for the statistical properties. We won't really go into what those are, but it is, it is pretty robust for example, the two problems that I mentioned. Okay. So let's see what trim loss is for least squares regression. Right? So I have samples xi, yi, and the standard training is to minimize the sum of squared losses. And trim loss would be the same thing, except that you minimize it only over a set S. Okay, so our simple idea is that if we knew the good samples, we could get a good model. And if we knew the model, we could select the good samples. So specifically what this is saying is that, instead of doing the two minimizations together, which is the principal thing to do, just do them in an alternating fashion. And doing each one in isolation, keeping the other fixed, is almost trivial. So the idea is to initially estimate a model from all samples, and then iterate between selecting a good set of samples, which means those that have the lowest loss currently, right? So that would just mean taking all the samples, ordering them by their losses, and keeping the tau n that have the lowest loss. And conversely, once you've done that, then you have found your set S, or I guess your set G, which is the good set. And then you estimate a model by minimizing only on the good set. Right? And this is standard model fitting. Right? All I have done is I have subselected the samples that I'm training it on. Right? So it works with pretty much any model setting where there's a loss function for every sample. Right? And we have a way to train a model and retrain a model based on samples. So that's the idea. And now what we're going to do is we're going to explore the effectiveness of this idea, both theoretically and experimentally. Right? So I'm first going to talk about linear convergence of to the true model for mixed linear regression, and I'll tell you what that is. And then I'll also show you some results for kind of larger neural network machine learning models. All right. Okay, so let's look at the problem of mixed linear regression. This is a pretty standard problem in statistics. And so what mixed linear regression is that we have samples xi and yi, but unlike standard linear regression, they now come from two or more linear models, right? So each sample xi, yi comes either from a theta 1 star, or a theta 2 star, or a theta 3 star, and so on. Right? So these unknown, these theta stars are unknown parameters, and all we have are samples xi, yi, and for each sample, we don't know which of these parameters it came from. Okay. So this is a simple regression instance of bad training labels, right? I mean, one can think of theta 1 star as corresponding to one of the labels, and theta 2 star as corresponding to some other label, and so on. And we don't know which labels are bad. So this is the mixed linear regression problem. And I have shown in this figure here a kind of toy example of mixed linear regression with two components, right? And with each one labeled red or blue. But in the actual data set that's given to us, the reds and blues have all been converted to blacks. Right? So we don't know which point corresponds to which linear model. All right. So in this case, what does our method tell us to do? Right. So what we will try to do is we will not try to find all the theta stars simultaneously. Instead, we will just try to find one of them. Okay. So let's say we have 3 theta stars. We'll ignore the fact that we have 3. We'll just try to find one. Right. But we'll be cognizant of the fact that that one theta star that we want to find does not fit all the data. So we want to find the tau n samples with the smallest squared loss and keep iterating with our method and hope that it converges to one of the theta stars. Okay. Right. So what we do need for this is we need an estimate of tau, right? So which means we need to know how many samples correspond to one of the theta stars. Right? We obviously we don't need to know which samples correspond to the, to that theta star, but we do need to know, for example, that every theta star has at least 20% of the samples. All right. So let's see what this method does in pictures. So I start with some initialization. It could even be random, right? And so let's say my initial guess for the theta star is this line. And now what I'll do is I'll draw a band around the line to see which are the points with lowest loss, right? So the perpendicular distance of a point from the line is the squared loss, right? And so I'll draw a band around the line until I get, let's say, 30% of the points if tau is 30%. Once I do this, then I will ignore all the other points and refit only to the points that are within the band. So once I do that, I get a new line, and then I get a new band, which again retains 30%, and I refit to that, and I get a new band and a new line, and I keep doing this. Right? So every time I get a new line by refitting to the band, and then I get a new band by seeing the points closest to the new line, and so on. We can theoretically analyze this procedure, and I've stated the theorem here informally. The formal theorem is there in our papers. Essentially, what it says is that if I start from any theta, I will linearly converge to the closest theta star, provided that the fraction of that theta star is bigger than the fraction I use in my algorithm. Okay, so let me restate. So my algorithm, let's say, for example, is that I retain the 20% lowest loss samples. So my tau is 0.2. And now I start from some theta. So the first thing I need to do to see if I'm going to succeed or fail is to look at which is the closest theta. There are many theta stars that explain the data, and I'll see which one of them is the closest. Right? And if that closest theta star has a fraction of data associated with it, which is bigger than 20% of the overall data, then I will be able to converge to it linearly. Right? So in that case, I'm lucky. If, on the other hand, the closest theta star has a fraction that is smaller than the one I chose, I will not be able to converge to it. Right? Even though there may be some other theta which explains a lot of the data, if I have bad initialization and I end up near a theta which has a very little data associated with it, and in my algorithm I'm retaining a larger fraction of the data, I will not be able to converge to that theta. Okay. So that's what the theorem states. It kind of pretty exactly characterizes what is needed of the initialization and what is needed of the tau for the algorithm to work. And more formally, we have deterministic conditions on the design matrix X, as well as simplified conditions for, if the X's, for example, were drawn from IID Gaussians. All right. This is the linear convergence statement. So it says that if the theta hat, if at any given time I have a theta hat that's closest to theta 1 star, and tau 1 star is larger than tau, then in the next iterate, I will the distance to theta 1 star will decrease by a fraction c up to an additive constant sigma. Right? And this will hold true provided that the number of samples is bigger than the dimension divided by the square of c and the 4th power of tau. Right? So these are the simplified conditions I mentioned. for the case when the x's are IID Gaussians, right? So, which means x is a d-dimensional vector, and it's a Gaussian with unit covariance. So we see that. So we see a few things. We need more samples as we have a higher dimension. We also need more samples as the tau becomes smaller. And the more samples we have, the smaller the constant c will be, right? Which is the fraction by which it decreases in every time step. Okay. So now that we have this, the way we can solve a mixed linear regression problem is to start from a theta and hope we're lucky, and then peel and repeat, right? So say I choose 20% and I converge to theta 1 star, then I can choose my 20%, take those samples out of consideration, and try to do this again. So these are the results for mixed linear regression, which is a pretty simple setting. And for this simple setting, we can prove theoretically that that this process does actually achieve what we hope it will, which is consistent recovery of one of the underlying parameters in the presence of bad data. Right? So can this understanding carry over to deep learning? Right. So there is a problem with immediately saying yes, and the reason is that unlike linear regression, neural networks are heavily overparameterized, and they will fit all the training data. Right? Like if you run neural network training for several epochs, the training loss for all samples will be 0, whether they are good or bad. Right? So this has been observed in several recent papers, right? Which is that like if you take a training data set, if you give them random labels, neural networks can still fit everything. Right? So this is a well-known phenomenon, and so what this means is that this the approach we just mentioned, which works so nicely for linear regression, cannot be carried over as is to neural nets because of overparameterization. Right? So there's a simple fix to this issue, and the simple fix is to not run neural nets all the way to full training, but only to run it for a few epochs in the initial phases when you are trying to kind of narrow down the data set that you want to ultimately train on. Right? So you can think of our iterative method as going through phases where it's trying to figure out which are the samples it should train on, and then training on them. Right? So when it's doing this search over samples, it makes sense to only run neural network training for a few epochs instead of running it all the way to completion. So this is an empirical observation, but the idea is that initial epochs in training can differentiate between good samples and bad samples. Right? So here in this plot, I have 4 plots, right? So let's take the top left. Right? And so on the x-axis, I have the number of epochs of training. And on the y-axis, I have the accuracy. And this is again for CFAR 10 with the wide ResNet. And we see that, I have separated out the accuracy that the model achieves on clean samples and on bad samples. Right? So I've taken my CFAR 10 corrupted data set. I started training it. I started training a model, and I evaluate the loss on the training samples as the model parameters update. Right? And I find that, as we plot the accuracy, we see that the accuracy goes up for the bad samples, and it kind of plateaus or goes down for the clean samples, and the overall accuracy over the entire data set is going up. Right? But we haven't plotted that here. Right? But what we do see is that in the initial epochs, clean samples, because they represent a majority of the training samples, do have a higher accuracy, which means lower loss. Right? And so if I keep training for a large number of epochs, I will indeed not be able to find out which is a good sample and which is a bad sample. But if I stop it at initial epochs, we can actually distinguish between good and bad samples, at least on average, and clean out the data set that way. So for deep image classification, essentially what this means is that the algorithm in this case would be to train the classifier on on all samples for a few epochs, and then choose the best tau fraction, right? And the way you choose best is that you look at the training data again, you evaluate the loss for each of the samples. For the samples in each of the labels, right? So I take all samples that in my training data have been labeled as horses, and I evaluate the loss on each one of them, and then I pick the best tau fraction of them, and I do this for every label, and then I retrain my model again for a few epochs on those chosen labels and keep repeating. Right? And as I keep doing this, I keep increasing the number of epochs I go for. That makes sense. Right. Okay, so here we show some results on kind of 3 data sets: a small data set, a medium data set, and a kind of relatively larger data set, which is MNIST, CFAR10, and CFAR100, for 3 methods. Right. So the first method, which we just call baseline, is something which does not recognize at all that there's bad training data. Right. The second one is ITLM, which is our method, and the third is the oracle, which knows the bad labels and ignores them. Right. So so those are the 3 methods, and these are 3 data sets. And now what we do, sorry, go ahead. Is there a question?
Yes. So the question is whether tau is a constant.
Right. So tau is a parameter of the algorithm, and we actually need to know this a priori, right? So, or at least we need to know a bound on it. So, for example, if I use a tau of 50%, then I'm implicitly assuming that at least 50% of every label is good samples, right? So this is something that needs to be known a priori, and it's a parameter to the problem. Okay. Right. So here we have many different levels of corruption for the data set, right? So, there's 60%, 70%, 80%, 90%, which is on the left-hand side, right? So this is the percentage of samples that are good, right? And the other samples have been systematically corrupted, as I mentioned before. Right? And so we see that, the baseline accuracy drops quite a bit in going from 90% to 60%. The oracle complexity, the oracle accuracy also goes down simply because we are decreasing the number of training samples that are available. So even though the oracle knows which samples are good and knows to ignore the bad ones, its accuracy still goes down a little bit.
So there is one more question. Satya, do you want to ask the question?
Yeah. So how are these models being evaluated? So are we just evaluating on the on the good training data?
No. So what I've shown here, so that's a good question. What I've shown here is the 60, 70% and so on is the fraction of good data in the training data, but the results are on new test data, which is completely clean.
Okay. Yeah.
Right. So this is a setting where the training data is bad, but the test data is clean, right? And I mean, as it should be, I guess.
Yeah.
Yeah.
Thanks. Okay.
Right. So kind of the upshot in all 3 of these things is that this kind of simple modification of training, which is to like iteratively throw away bad samples, can actually significantly rescue the accuracy of pretty much an off-the-shelf model. Right? Okay. Let's turn our attention to an unsupervised setting, which is GANs. Just a quick primer on GANs, although I'm sure most people by now know what they are and how they're trained. So the idea for GANs is that so the objective of GAN training is to make something called a generator network, which what you want it to do is that you want to give it a random vector, typically spherical Gaussian, and it should be able to generate an image which looks like an image from a particular data set. So in this case, let's say we want to be able to generate fake handwritten digits, right? And so, I want a neural net which I can give it a random vector, and it'll generate for me an output that looks like a handwritten 0, 1, 2, or so on, right? And so the way one way that such generative networks are made is by training it in an adversarial way. That's GANs. So what is done is that you pair this generator that you want to make with a classification, with a binary classifier, which is called discriminator, right? So the generator takes random vectors and tries to make an image. What the discriminator does is it takes in images and tries to label them as essentially original or fake, or real or generated, right? And then we need to simultaneously train the generator and the discriminator, right? So the way the discriminator is trained is that you feed it either a generated image or a real image, and try to make, and the point of discriminator training is to try to make it as accurate as possible on being able to distinguish between real and fake. And that is trained in competition with the generator. And the objective of the generator training is to try to fool the discriminator as well as it can. We want to do we want to make GAN training more robust when, for example, the real images are not all from the data set you expect. Okay? So in building up towards this, let's think about what theta means and what L theta is. So theta in this case is a set of model weights of both the generator and the discriminator, and L theta is the loss given by the discriminator. So given any sample in the training data set, right, I can always put it through a discriminator and I get a loss, right? So that is what we will call L theta. All right. So now we are thinking of GANs with mixed training data, right? So we have a data set that is 20% fashion MNIST and 80% MNIST, and we don't know for any given sample whether it comes from fashion MNIST or MNIST, right? They're unlabeled. And what we want to do is we want to make a generator which generates handwritten digits. Right? We do not want to generate fashion images, and we do recognize that fashion images exist in our training data. Right? So this is the challenge we want to solve. All right. So as I mentioned before, if you do not recognize that, or you do not account for the fact that the training data is bad, then it leads to very poor results. Right? Where not only are the images, not all handwritten, but even the handwritten parts of the images look like they're very poor quality. Okay. So the issue in GAN training is that we don't know what the actual likelihood function of the real data sample is. Right. So the idea is to use a surrogate, which is the output of the discriminator. Right. So the L theta in our case is the loss at the output of the discriminator, and so that gives us the algorithm, which is that train the GAN with all samples for a few epochs. Right. And then the way you filter out the training data is by running only the discriminator on every training sample. Right. And the discriminator is a binary classifier, right? And you're running it on only what you think is real data, right? So it should always be labeling it as real, but for some of them it does, and for some of them it may not, right? And you pick the ones on which the current small epoch discriminator is quite accurate. And then once you do this, you have your filtered down samples, then you retrain the model on only those samples, and you keep going. So now I'd like to show what the output of this process is for MNIST, for 80% MNIST and 20% fashion MNIST, right? So kind of iteration 0 is the baseline.
Sujay,
Right?
there's
Like,
a question.
yeah, sorry, go ahead.
Razi, you can speak. Okay, so let me relay the question. So it's asking, how can we be sure that we don't miss hard but correctly labeled training samples by removing samples with high loss values after a few epochs of training?
Yes, that's a very good question. You cannot get them. And this is why, if we go back to the labeled case, right, like you will see that even after, that ITLM is not as accurate as the Oracle, right? And the reason might well be that things which are hard to label but accurately labeled have been treated as outliers, right? So I think that's a good question, and that is something that is present in any method that tries to tries to account for outliers, right? That there'll be some correctly labeled things that will be labeled as outliers because they're on the boundary of what is legitimate. Does that answer your question?
I think yes.
Okay. Yeah. That's a good question. Coming back to GANs, so we see that after doing one iteration, which is kind of like an outer loop to training of our method, right? So the first iteration here is we trained the discriminator for a few epochs, and then we use a discriminator to remove high loss samples from the MNIST fashion MNIST mix, and then we retrained again, right? And the first iteration is the output of that retraining.
So there is one more question. Yonglu is asking, what loss function do you use for GAN? And it's a bit odd to have a loss for just one training sample.
It is a bit odd to have a, no. So, you mean what is the loss that the GAN is trained with? So I believe this was trained with Wasserstein loss, if I remember correctly. And it's a bit, yes. So I guess in training, losses are evaluated on a batch basis, but you could, you could put a single sample through this discriminator to find its loss function.
Yeah, my question is actually, so if you just use one sample, that will be just finding somehow the map estimator of your distribution in some sense. But I mean, in the end, you want to find the entire distribution. So I think training this with one sample is a bit,
no. Right, yeah, no, sorry. I'm not training it with one sample. So when I train it for a few epochs, it's trained in the regular way. But then I'm only using it on a sample by sample basis to accept or reject samples for the next batch of training.
Right. Okay, so you order the samples, the most likely samples.
Yeah.
Which are similar to
so say, for example, my tau is 50%, right? Mm-hmm. Then I will take my kind of current discriminator. I'll evaluate it on every one of the 100%, and then I will take the 50% that have the lowest loss. But then when I train again, I am training it in the regular way, which is not by a single sample.
Right. Okay, thanks.
Okay. Yeah, and right. So I guess what this figure shows is that by the fifth iteration, we have managed to clear out any generated image of any fashion MNIST from generated images, right? So what this shows is 32 vectors picked randomly from the input Z space of the GAN, right? And it's the same 32 vectors for all of them, right? So those vectors become better as the iterations go forward.
Right? Sujay, a quick question.
Yeah.
So can you briefly compare this approach with something like learning to reweight, which also learns how to reweight examples? Is it just because is the difference between soft and hard decisions?
Right. Yeah. So that's a good question. We have not tried to evaluate whether soft down weighting will be better or not. Yeah. So I don't have an answer as to whether soft is better than harder or not.
Okay.
So we tried the same thing with a slightly more challenging data set, which is where we want to generate faces from celeb A, but our training data set for the GAN that we will use has 30% of the images coming actually from CFAR10. Right? So if all your input images are faces, then as we all probably have known, have seen or heard, you can generate pretty good quality faces. But now if 30% of the images that we think of as faces are actually not faces, then the quality degrades pretty rapidly, right? And so I would say the baseline looks quite bad, and a few iterations, helps things look a little bit better. At least most things look like faces, but obviously this is a much harder data set, right? And so it needs more. The approach needs more fine tuning. Right. So those were some qualitative results. We also have kind of more quantitative results on how good our GAN generation is. Right. So the way you can quantify something like the way we quantify it in this setting is that we do our ITLM method, so which means we have a discriminator at the end of iteration 1, a discriminator at the end of iteration 2, and so on. And hopefully these discriminators are getting better on the good data. Right? And so the idea is to run the final discriminator on the training data. Right? So if you run the final discriminator on the training data, and so if all our training data was good, which means there were no outliers or bad data, then what will happen is that the discriminator will be really good at identifying all those images as being good. Right? But if your original training data is bad, then the final discriminator will not be that good. Right? And so to summarize this table, we can see quantitatively as well that as we run more and more iterations of ITLM for both MNIST corrupted with fashion MNIST and celeb A corrupted with CFAR10, we do see that the final discriminator becomes more accurate on the samples that are actually good.
I had a quick question.
Yep.
Maybe I'm wrong over here, but looks like the training procedure induces some bias in the learning procedure because you're discarding some of the possible legitimate examples.
Yes.
So initially you presented some results on convergence. What was the convergence of the theta2? And is there any bound on kind of bias that you are incurring?
Right. Yeah, so that's very good. So it's definitely the case that the final results can be biased because hard samples, hard samples which are truly which have the correct label might still be ignored. Right. So my initial results were for linear regression, And, you know, so, I mean, I can go back to them. So if I'm just going back to the theory result. So the theory result was for linear regression. And essentially what it said, okay, this is it, for example, right? So there is a particular theta star. And what this is saying is that my estimate theta hat gets closer and closer to theta star under certain conditions. So here, the conditions for this for this version of the theorem are that the samples come from an IID Gaussian, right? And so effectively what's happening here is that because it's a simple linear regression setting and the samples come from an IID Gaussian, and we have enough number of samples, so you have that n is bigger than this number, that even though you know, some legitimate samples are considered outliers, they're not enough to bias it away from the truth. Does that make sense?
So we are, am I audible?
Yeah, I can hear you.
Hello?
Yeah.
Yeah, so in this case, are we assuming that the true model lies in the model class of R?
Yes. Theta star is
Looks like my internet connection is weak.
linear regression vector, and we are in the
Hello?
same model class, right? So, I mean, all these assumptions obviously do not or may not hold for neural networks, right? So the theory results are only for linear regression. All right. Yeah. So coming back to GANs, here's a failure case. So it turns out that if the fraction of good samples is not high enough, then even if we know what that is, the approach may not work. Right? So we tried the same example as before, but now it's 60% MNIST with 40% fashion. And so MNIST is still the majority, and we still are interested in generating digits, but we can't do it anymore with our process, even when we know that 60% is good. Right? So it will be interesting to find out, you know, or to get kind of a more theoretical understanding of what things, you know, of how big tau star can be before something fails. But we don't have that currently. But there definitely exists a tau star, which is too low. All right. So in summary, you know, we propose a simple idea, which is to iteratively learn from the best, right? And it can be used for pretty much any machine learning setting where there is a per sample loss. We provided some theoretical justification for it in the setting of mixed linear regression. And we also provided some empirical results for deep image classifiers and also deep generative models. In our paper, we also have some results for backdoor attacks. I didn't have time to go over it in the talk. And kind of at a higher level philosophically, you know, what we advocate is to focus on the best samples for robustness, right? And this is in direct contrast to something like boosting, where you know, we iteratively focus on the worst samples, right? So if you remember what boosting is, right, then it's like we have a model, and then we reweight samples to give higher weights to those that have high loss, so that we can you know, decrease the loss of the highest loss samples. So that is in direct contrast to what we're advocating here, right? I mean, obviously the settings are different because I don't think people consider robustness in the context of boosting. So I think it's an interesting kind of problem direction, which is that can you get the advantages of boosting when you have bad training data? So I think with that, I'll finish, and I'm happy to answer further questions if there are any.
Thank you so much, Sujay. I have, so the question answer session can start. I have allowed the participants to unmute yourselves. Hopefully there won't be any noise because I've logged the meeting. So please unmute yourself and ask questions.
Hi, Sujay. This is Anand.
Hello.
I had a question about your sort of general paradigm. And if it sort of applies directly to like reinforcement learning when you have to do policy search and then policy evaluation. So that would be sort of your first step would be policy search because you can iteratively improve the policy that you're trying out. And then the second thing is you have to be able to evaluate loss, which is sort of like policy evaluation, but except not in the same. Like, is that meta principle in there? So something like that. So.
I'm a bit hesitant to say yes, because in RL, if I understand, so we have to interpret it correctly. Like, what would be a sample? I guess a sample would be a trajectory, right? And the thing in RL is that the trajectory depends on the sequence. You pretty much don't retrain with the same trajectories again and again, right? Because your trajectory depends on the actual actions you take in every step. So I don't have a good answer, but I would be surprised if the answer is just yes for applying.
No, I just meant sort of, you know, if you thought there would be some use of this idea there, but thank you.
Yeah. So the answer is I'm not sure. It's a good question.
Any more questions?
Hi, Sujay. Yeah, I have one more question. So how did you choose tau in your MNIST experiments, the initial experiments that you showed?
Oh, we just assumed we know tau, right? So, I mean, my MNIST experiment was a hand-engineered experiment, right? In the sense that I knew that it was 80% MNIST and 20% fashion MNIST. And so we just chose a tau which was less than 80%.
Cool.
Yeah, and so, you know, kind of empirically, the way to choose it, if you don't know this beforehand, is to keep a holdout set and to keep increasing tau until your accuracy on the holdout starts decreasing. Yeah, if that makes sense.
And also, like, how many iterations did it take to like converge? Because like every time you are losing like 1 minus tau% of the data there.
Oh, yeah, that's a good question. Sorry, I didn't clarify. I'm not losing tau% every time. You know, I put everything back in when I reevaluate.
Oh, I see. Okay. Yeah.
So finally, I'm finally losing only 1 minus tau% at the end.
Okay, I see. Okay. Yeah.
So one more quick question.
Yep.
So so let's say if you have corruptive data that are much easier to fit. So if you stop early and try to see what are the good data points and what are the bad data points, you might see the case where your neural network already fitted all those bad data points first, and then still trying to fit those clean but difficult to fit data points. So it's not easy to choose when to stop and trim these data points. So do you have any suggestion or do you have any idea on that?
Right. So, you know, we are using very limited information, right? We are just using the final loss on the data points. And I think with this, it's not actually possible to fix the issue that you just raised, right? And I think that's reflected in the accuracy, in the fact that ITLM, even after several iterations, is not as good as the Oracle, right? Yeah, so you know, I mean, kind of the simplest setting to think about this is just in finding the mean of a bunch of Gaussian samples with some outliers, right? Like you can keep trying to fit the mean to a smaller and smaller number, or to a subset of the points, and you know, I can very easily put adversarial outliers so that I'll never get consistency. Yeah, so there is no real way to do that, you know, but the hope is that, you know, so the neural network setting, the supervised neural network setting we studied this in was where the errors were only in the labels and not in the features, right? So if you allow errors in features, I think this approach is not so good. But if you allow errors only in labels, which could be like sloppiness in data collection, then there might be hope because the adversary is not as powerful.
Thanks. But even for unsupervised learning, let's say if you are going to do the other way around. So I think most of the experiments you showed today was you start with the MNIST data, but add some fashion MNIST, or you start with CellLab, but add CFAR. So you're adding more difficult to, I don't know whether the other way around, but
yeah.
Oh, I think. So
yeah.
You,
and I mean, I think what you're saying is, like if you take a handwritten digit 6 and add some bad pixels to it, right?
Exactly. Yeah.
Yeah. So that's what I would call errors in features, like it's errors in the X. And yeah, there is no, I don't think this approach is the right answer to that, right? This approach is the right answer to corruption from a completely different data set.
Got it. Thanks.
Yeah.
I had a quick question. So given that this approach is so versatile and model agnostic, I was wondering if you had looked at non-neural network examples, like you talked about robust PC and all. So in those classical settings, how does this perform as compared to those existing methods, robust PCA or robust regression, any of those?
Right. So, I presented the results here for mixed linear regression, but similar guarantees are also possible for robust mixed linear regression, which means that there are some xi-yi pairs that come from one of the thetas. And then there are some xi-yi pairs that come from no theta at all, which means that they are just outliers. Mm-hmm. Right? And so that covers the case of robust regression as well. So for robust regression, we have results in the paper, and they are pretty close to being, state of the art, at least for random Gaussians. And they have worse dependencies for fixed designs. We have not studied this algorithm for robust PCA, but my hope is that it would not be too bad, right? Because both PCA and linear regression are things where the model class is pretty tightly constrained. It's only when you get to things like large neural nets that you run into issues with overfitting and so on.
Cool. Thank you. Yeah.
Let's take one last question and then we can take the other questions offline.
I have a question so do you think this approach is agnostic to the starting point from where we start for the parameters? Because if you consider the case of the mixed regression, where we have two sets of parameters, one is for the malicious or the noisy examples, and the other one is for the original data points. Then if we start from a point which will give you loss lower on more of the malicious points, then it might actually converge to the malicious examples.
Yeah, so that's a good question. And this theorem actually tells you what's a good and bad initial point. And there are definitely bad initial points, right? So what the theorem says is that if I start from a theta, then I can be lucky or unlucky, right? And what does lucky mean? Lucky means that, once I have a theta, I can only go to the closest theta star. And even that I may not succeed, right? So I will succeed in going to the closest theta star as I do iterations of my method, only if the tau that I am using is smaller than the tau star corresponding to that closest theta. Does that make sense? Right? So if I'm using 30%, which means if I think 30% of the data is explained by by the closest theta star, then if the closest theta star explains less than 30%, I will not get to it. It's only when it explains more of it, right? So initialization definitely makes a difference. And for linear regression, we can characterize when it, what is good and bad initialization. Now, empirically, in these neural examples that I mentioned, we always initialize by just fitting on the entire data set. Right? And if we don't do that, then we actually do not get good performance.
Okay, so now I will unmute everyone so that we can thank Sujay.
Okay.
Thank you very much.
Real virtual applause. Okay.
So, sorry for the disturbance in the beginning of the talk, but the rest went very well. Thank you so much. And we'll meet again on April 17th.
Okay. Thank you.
Thank you, everyone.
Thanks.